Okay, this is my Quidio number 5. The basic question of this Quidio is talking about the daily intakes of calcium in 38 women between the ages of 18 and 24 years of age. Part A of the basic question asks to display the data using a histogram and describe the distribution of calcium intakes for these women. So they gave us 38 samples of the daily intakes of calcium in milligrams, and they were all in the 600s to 2400s. And I put all those numbers into L1 and put it into this histogram, and as you can see, it is very skewed to the right, and that bar all the way to the right is an extreme outlier of 2433. Part B asks to calculate the mean, standard deviation, and standard error of this data set, and since I already had those numbers plugged in, I went to stat and then calc and then one variable statistics, and I got, for the mean, I got 926.0263, and then for the standard deviation, I got 427.2295, and then for the standard error, that is standard deviation over the square root of n, so for that I got 69.3058. Part C asks to find a 95% confidence interval for the mean, but first we have to figure out if it's a t-test or z-test, and this problem would be a t-test, and for that you use degrees of freedom, which is on table C, which is not the same thing as a z-score, which is what we use for z-test because that's found on table A. So totally different things. Make sure to know the difference. For the degrees of freedom, it's n-1, and we have 38 women who were sampled, so it's 38 minus 1, which is 37, but we always round down when it's not in the textbook graph that they give us, so we round it to 30, and then you find the 95% number that correlates with 30, and that is 2.042. From that, we write out our confidence interval formula, which is mu plus or minus t multiplied by the standard deviation divided by square root of n, which after you plug in those numbers, that looks like that. And then the confidence interval comes out to be 784.5039 and 1067.5487. Part D then asks to take out the highest two values and recalculate the whole 95% confidence interval. So the highest ones I found were 1933 and 2433. So once you take those out, you can do the same thing because you take those out from L1. So you can do the same thing on your calculator. Just go to calc and then one variable statistics, and you get 856.1944 and for the mean, and then the standard deviation is 306.7296. And then you have your same formula there. You plug in your numbers, and then you get 754.5883 and 957.8005. And then it also asks, what did you notice about the difference? And if you look between those numbers, they are almost very similar. The lower numbers, there's like 30 in between those. So I said the overall confidence interval is lower than the original. The advanced question is a probability question. So it asks, you play 2 games against the same opponent. The probability that you win the first game is 0.4. If you win the first game, the probability you will also win the second is 0.2. If you lose the first game, the probability that you will win the second is 0.3. So all of those numbers are hard to remember for me, so I put them into this little graphic sort of thing. So W for win, L for lose, obviously. So the probability that you win the first game is 0.4, which means that the probability you lose the first game is 0.6. And then they give you that if you win the first game, the probability you will win the second is 0.2. So that means the opposite of that, which would be losing the second game, would be 0.8. And then you do the same thing with the 0.3 that they give you for if you lose first, because that gives you 0.7 for losing again. Part A asks if the two games are independent, and the answer to that would be no, because the probability of winning the second game depends on if you won the first game or not. If they were independent, then the probabilities would not change. Part B asks, what is the probability that you will lose both games? So we can go back up to our little chart, and it's 0.6 for the first one and then 0.7 for the second one. So you multiply those and you get 0.42 or 42%. Part C asks, what's the probability that you win both games? So again, we just go back to our chart. So that'd be 0.4 times 0.2, and that ends up being 0.08 or 8%. Part D asks for a probability model for X when X is how many games you win. So X goes on top, and then probability of X is on the bottom. And if you win 0 games, it's 0.42. And if you win 1 game, it's 0.5. And if you win 2 games, it's 0.08. The last part of the advanced question asks for the expected value and the standard deviation of this problem. So I like seeing both of these at the same time because it's easier to put the numbers together. What you do for expected is you do the value of X times the probability of X, and you do all of those together, and that adds up to be 0.66 or 66%. For standard deviation, first you have to do the mean that you get minus mu. So we have each of those means that you could possibly get, and the mu, which is 0.66 because that's our expected value, and those subtract to be 1.34, 0.34, and negative 0.66. So what you do from there is you take that number and square it and then multiply it by its probability that we stated up here in this graph. So that ends up to be 1.34 squared times 0.08, and that equals 0.384. And then you use that and you take the square root of that, and it ends up being 0.62 or 62%. The AP question asks about the U.S. Department of Agriculture and their experiments of using different methods on contamination in beef of E. coli bacteria specifically. So this is a phantoms problem, so there's going to be a lot of work. I wrote the labels out a little bit just because it helped me see it, but don't do that on the test, on the AP exam, because that could confuse your grader and make them think that you don't know what you're doing. So the first part we do is parameter, and that would be the amount of E. coli bacteria in beef, because that's what we're testing. And then the HO and the HA are our hypotheses. So the HO would be that the mean E. coli detected through method A would equal the mean E. coli detected through method B, and then the HA would be that they are not equal. And so for assumptions, SRS is given because they told us it was randomly sampled, and then we're going to assume independence and we're going to assume normality, but we need to proceed with caution because it was only 10 specimens of each type of beef, and that's a pretty small number for N, so we have to be careful about that normality. So this problem would end up being a 2-sample t-test because they don't give us the population and they also have 2 different samples. So that would be a t-test, and it's this giant scary formula, which I'm not going to read, but you can. And then we get to plug in all those beautiful numbers. What you do to find all those numbers is you plug in the data that they gave us into L1 and L2, and you can find the different means and standard deviations. And the N for both is 10, because they told us it was 10, and there's 10 on the graph. So that all ends up to a t-score of 0.079. Again, since it's a t-test, we use degrees of freedom, so that's n minus 1, which is 10 minus 1, so we use 9, and then you're going to go to 9, and you're going to try and find where 0.079 would fit in between, but the very first number on the 9 row is higher than 0.079, so that means that our p is going to be greater than 0.25%. Just 0.25. The very last part is the giant statement that you have to put everything you just did into to make sure you get full credit. So, we will fail to reject the hoe that the mean E. coli detected through method A is different than method B based on the t-value of 0.079 and a p-value of p is greater than 0.25 with an alpha level of 0.05. They did not tell us that in the problem, but that is the assumed alpha level, so that's the one you want to use if they do not tell you. Just a little way to remember is phantoms, and you always make sure your statement is in context because you can pretty much set up a structure for this statement that you have to write for every question where they ask to provide a statistical justification or evidence or significant difference. Those phrases all mean to do phantoms. So don't write out phantoms on there, but remember that is the system you use.